Hi, my name is Zubair Hussain, and today we will be discussing about the term paper of our course. In this, we will be discussing about five basic families of algorithms, namely divide and conquer, dynamic programming, greedy approach, backtracking, and branch and bound. These are the five algorithms which we will be going to talk about today. So first of all, let's start with the divide and conquer algorithm. In this, what we do is that we divide a larger problem into various small subproblems, and we keep on dividing into smaller problems till the time we are able to solve the smallest problems. Okay, so this is a top-down approach where we have the complete problem, and then we will break it down, and then break it down to the last level so that we will be able to solve this problem. Okay, so for breaking down the problem, we need to define a recursive relation, and we can use this recursive relation to divide the problem. And finally, we can combine the solution of all of these subproblems to get the final answer of our larger problem. This sort of algorithms works best if our subproblems are independent from each other and are not overlapping, as is the case with the binary search or the merge sort algorithms, where the subproblems are not overlapping to each other. We can solve the subproblems independent of each other, and they are independent. So divide and conquer work best in those kind of settings. However, it doesn't work if the subproblems are dependent on each other or overlapping, that is one, or if the subproblems are almost of size n. Okay, so let us say if I have a problem of size n and I'm dividing into a problem of size n by 3, then I don't want 11 problems of n by 3. Okay, I want 2 or 3 problems of n by 3. So that is whatever. So for example, whatever decrease we are having, it should be complement. Creating 2 or more problems with almost size n will not also help. So this is all about the divide and conquer algorithm. Next up is the dynamic programming algorithm, which is used primarily because of the subproblems which are not independent and which might overlap with each other as well. For example, the Fibonacci problem, which we have, wherein the fn equals to fn minus 1 plus fn minus 2. So here the fn minus 2 is itself related on the fn minus 1. So the recursive relation, the subproblems are overlapping, as well as because of that dependent on each other as well. So for that cases, dynamic programming is a good way to handle. Unlike divide and conquer, it is a bottom-up approach where we will first solve the smallest problem and then combining them to raise one level high. So for example, in the Fibonacci problem, we will first have f0 and f1. Then from f0 and f1, we will calculate f2, store f2 in the memory. Then using f2 and f1, we can calculate f3. So for calculating fn, we need to only calculate n plus 1 terms rather than the 2 to the power n by 2 terms, which we used to calculate for if we want to solve this Fibonacci problem using divide and conquer. So storing the intermediate results benefits us in solving the overlapping and the dependence of problems using dynamic programming. The most common problems with dynamic programming is very useful is the shortest path problem, wherein we need to find the shortest path between the vertex I and vertices j, or the longest common subsequent identification, etc. But one of the disadvantage of the dynamic program is that we are storing all the intermediate results, wherein it might be possible that some of the intermediate results are not required for reaching to the optimal solution, and for that we will see how backtracking and the branch and bound algorithm helps along with dynamic programming in encountering some of these problems and giving us better time and memory complexity. Going with the flow, first we will talk about the greedy approach algorithm, and then we will shift our focus to the backtracking and the branch and bound algorithm. So the greedy algorithm is the most simple algorithm among the 5 algorithms which we are discussing today. In this, what we are thinking is that, let us say I am at time t and I want to know what will be the best at time t plus 1. So whatever best at time t plus 1 can only be judged using the conditions prevailing at time t. It doesn't matter what are the conditions before time t, it doesn't matter what are the conditions after t plus 1. So it takes a local decision, okay, based upon whatever is the available information at that point of time. A common example is the minimum spanning tree problem using the Prim-Skulls algorithm, wherein one is based upon the vertices and one is based upon the edges, wherein first we will initialize a vertex or an edge, and then we will add one vertex at a time or add one edge at a time and trying to traverse through through a tree and see if it completes all the points. So here we will consider one vertex or one tree at a time, one edge at a time. For example, let us say I am at vertex A, and let us say the cost for vertex 2, 3, 4 and 5 is, let us say, 5, 15, 10 and 2. Okay, then I will go with the vertex 5 because it has the least cost of 2. So my decision is only based upon whatever are the prevailing conditions at this point of time. Now then I can have 1 and 5, and after that I can see how going from 5 to 2, 5 to 3, 5 to 4 impact our result. But the primary thing is that the decision is taken only basis upon the prevailing conditions, not on the past or on the future. Next we will discuss about the backtracking algorithm. It's a general algorithm concept wherein it says that you can drop a candidate if you think that that candidate will not lead to the optimal solution. So this is what, along with the dynamic programming, you can use backtracking to solve many of the problems. So for example, let us see for our 4 queens problem. Okay, so here if you can see that I have first placed the first queen in the first row, then so the first queen in the first row is in the first column here, second column, third column and fourth column. So now if I will go with this branch, then I cannot place queen on the first or second. Okay, I can place on the third or fourth. So I have placed on the third. Now in this kind of scenario, if I have placed first queen here, second queen here, there is no possible position for the third and fourth queen. So I can just drop this branch and backtrack to this and then proceed with this child. This is what is backtracking is all about. That is, if you think that this child will not be able to give you the optimal solution, backtrack to the parent node and go to the next child. Forget about this child for now. So the backtracking algorithm can be used for the Sudoku problems or the n queens problem. Here we have used the 4 queens problem for now. Now let's go ahead with the branch and bound problem and see how it's different from the backtracking. The primary thing is that in the backtracking, the constraint is defined by the problem itself. For example, the queen cannot be in at all these places. So the constraint is already defined by the problem, whereas in the branch and bound you need to define a measure of a bound. Okay, and then you need to evaluate all the nodes with respect to that bound. That is evaluating evaluating is easy, but making bounding measure, it's the most difficult task because you want it to be inexpensive to calculate but should also be effective in selecting the most promising partial solution so that you will lead to the optimal solution. Let's see this classroom example wherein we are comparing the solution provided to the knapsack problem using the backtracking problem algorithm and the branch and bound algorithm. So in the backtracking algorithm you will see that we are neglecting this, okay, because it is the 17 kg and the constraint is that you can have only 16 kg. So you can calculate till here. Here also we have dropped this, okay. So similarly we have dropped, and then finally we have seen that this is giving the optimal solution, okay. Now the branch and bound can significantly reduce the number of nodes. You can see that is the number of nodes are way higher here case, but the number of nodes are less. So here we need to calculate the bound. So here the bound is 115, okay. So you will just see how the bound is moving. So for example here you can see that the solution you have obtained is 90. So if the profit we have obtained is 90, then there is no meaning of bound to beta2. So you can drop all of these nodes. So this is how you can define a bounding function and use it to drop the non-promising nodes for your example, okay. So that's all about the 5 algorithms that we have discussed. Thank you very much.